So this is our weekly seminar in a bit of unusual setting today. And we have two topics to cover. One is Gemini 2, Google's recent release of a state-of-the-art model, which they say performs comparably to Llama 70B while being 27B in size. This is Gemini 2. And the second topic is another version 2 release. It's LLM Leaderboard benchmark, which is like a reproducible, well-known benchmark or other suite of benchmarks of language models, which they just like a few days ago updated to reflect that the previous benchmarks were saturated. And since we are often in the business of benchmarking like models to benchmark our results, I think it's useful to look at it. Okay, so our first thing is Gemma 2. I actually have like two articles here. One is the press release. This is what we'll cover first quickly. Also, I have to start the timer. Please start the timer. Yeah. And the second is that like technical report paper. Right. So one thing I'd like to highlight in the press release that actually there are quite a few variants of Gemma, like same as with Llama. Like they have, I think Meta has a few fine-tuned Llamas as well. Facebook has a few fine-tuned Llamas, and then Google has a few fine-tuned Gemmas. They're quite different. Like Polygamma is computer vision, for instance. And we have 9B model and 27B model. 9B model is better than Llama 8B. 27 billion is comparable with Llama 70B. And what's interesting here is that they officially target fine-tuning and inference at full precision on a single GPU. So with Llama, I had to quantize heavily. Here they support full precision on a single GPU. Or TPU. We'll get to that. Okay. I think it's more, on one hand, yes, we literally reduce the cost by 8 in dollars. As in, to run Llama 70B, you need to run Llama 70B, you need I think 800 with NVLink, and then to run Gemma, you need one 800. Which is actually a bit of a comparable price right now, because this is the latest generation, this is the previous generation of GPUs, but this reflects an interesting trend that people start targeting lower models increasingly. This also connects to recent releases by... Where's the black marker? This also connects to recent releases by Microsoft, who released the Pi 3 model, and Apple, which released its Apple AI model, which are also very small, 2B size. So this is an overall trend of well-performing small models.
I got this one. I got this one, but I can't fix them. So, okay, you can use one to draw new generation instead of one frames for the. But where is the preference?
Yeah, so this is both easier, as in it's easier for developers, and it like it's going to be cheaper soon because like this generation is going to become the old generation soon.
Same though.
This will become obsolete soon. So like this is not useful right now. This reflects a trend which is going to like to work in like 2 years time. As in costs go down in 2 years time. Kind of.
Okay. So page 120, page 100 they have 80 gigabytes of RAM. Yeah? So here we can train on one page 100, but it's a bit slower.
Yes, that's exactly correct. Yeah. So sorry about that.
Okay, so that will it.
Okay. Yeah, I sort of assumed that they have like some special optimizations which only require and which only work on an 800, but actually that's not right. Yeah, it works on an 800 so. Okay. So then we have like that it works with everything, like deploy on everything, the usual thing.
Good.
And I think this is about the extent of the press release. Just one other thing I want to highlight is this like slide here is that they evaluate, like this is a section they call safety, and they evaluate on toxicity prompts. Like, I don't know, like workspace toxicity and like discrimination. This is like their safety section. I mean, like no legible benchmarks about cybersecurity, about jailbreaks. Yeah. Okay, so that was the press release. Now on to the tech report. There's a bunch of ground to cover here. So my 3 highlights from the abstract is that they actually have a 2 billion model too. They use some ML tricks. And the last thing is I was kind of continuously surprised that no one was doing that before, because it makes so much sense. They train their small models, not like just retrain them. This is normal training process. Rather, they train them with distillation from a large model, and like this makes so much sense. Okay, so what do they say in an introduction? They say that everyone gets performance from just throwing computers at the problem. But as the Shinshua paper showed, Shinshua paper is one we covered at one of the previous seminars. It's about the trade-off of compute. Trade-off of train for more epochs on the same data versus add additional data, like how to trade this off. As the Shinshua paper showed, throwing more compute only scales logarithmically with that set size. And so Llama 3 doesn't actually improve state of the art that much, despite eating up an enormous amount of data. And so instead of throwing more compute at the problem, we suggest some algorithmic advances. And our algorithmic advance is exactly training with distillation. And like what training with distillation does, for those who are not familiar with the term, instead of having, I think it's useful to introduce another term which I'm going to use.
So just understand it's everything the same, but it's number of parameter. These models are big, but these models rise faster. So like,
what is this axis?
Performance by benchmark, like extra 5. What?
Yes.
It's like all right. Okay. New models like this one.
Yeah. The idea is that we like keep the same number of parameters, but do something to improve performance.
Yeah, and then that's it. As I understand you correctly, small models show the bigger horizons per color.
That's correct.
Okay.
I mean, like this is actually not quite a correct picture. It's more like there is like some frontier of performance, and it's kind of like we were here, and like now we're here with small models, and like this like so like, yes, the largest delta, but like we have also quite a bit of delta here. Okay. Yeah, so introduce two ML terms here. Two NLP terms, I think, actually. Also, this sure as hell isn't going to be heard on the recording. So, term one is perplexity. Perplexity. So, first, but okay.
Go on, Dermot.
Yes. So this is very basic. This is just conditional probabilities. So, like, we have a sentence. Sentence goes like, "I see you, cat," and we can hide the following tokens, and we have a probability distribution for the following tokens, and then like we have like the actual ground truth token. And we can model this by saying that we have like the first token probability, like let's call it probability first token. Down for this. So we have probability of the first token, that we have a probability of the second token, given we have this first token. And then we have the third token, given we have this zero. And so this sentence is essentially a chain of conditional probabilities. And this is exactly perplexity. Okay. Like what this means is that we want to train a model such that this kind of sentences has low perplexity because it's like a good sentence, and the kind of sentences which are like blah 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 blah, cloud green follows all, has high perplexity because it's a bad sentence. I'm sorry, this is actually this is negative perplexity. Yeah. So like this is it makes yeah. Is like, does it work? What? Okay. Well, does this work?
Yeah, but I'm trying instead what's that? Okay, we have one another parameter here that benchmark.
Yeah, this is the criterion that base models are trained on.
Models what?
That base models, like foundation models,
Okay,
are trained on. And the training process goes like, you give it the first token and ask it what's next.
Yes.
And like, you're like, actually, it was that. So like, it says that like, I don't know, 30% probability that it's rain, 20% probability that it's cat, and 50% probability that it's blah, 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 blah. And you're like, actually, it's 100% cat on this example. And so update accordingly.
but that's why did I'm not sorry, you started to
Yeah, why am I introducing that? Because it is the key to training large language models. Like it is the key. It is the objective. It is what everyone is doing.
okay,
And I will need it later on to talk about benchmarks.
okay, so your goal to get the low perplexity in every aspect of the model. So you're like when you go how it goes, like when you run final tests, you do data set of questions like 100 times, and you expect like in 95%, 95 cases, you can receive the same answer, right? So this is the case, there is low perplexity.
It's calculated in a different way. As it's a condition, even it's a bunch of conditional probabilities. For each sentence, I can compute the perplexity. So I don't get an answer. I get a number, which is perplexity for this sentence, for this model.
Okay. Okay, let's try.
Yeah, the one other thing I want to say is that the scaling laws are formulated in terms of perplexity. And perplexity is basically translates to quality in very broad sense.
Good.
So if you have low perplexity, you're good at many kinds of tasks empirically. So that's perplexity. And even the other side, I guess, we can that. At least we know that. Another term I'd like to introduce is knowledge distillation. This is connected to perplexity, which is why I chose perplexity first. So I just said that the normal training process is you give a sentence like I see a what, and the model gives you some probabilities, and you're like, actually a cat was 100%. So in technical terms, how the paper calls it, you have a one thought vector for the right answer. And the idea of distillation is that you have another probability model. So at this step, you don't give it this kind of vector, but instead you give it rain 0.01% and green. Okay, maybe let's make rain I see a rain. Well, kind of makes sense. Green actually makes more sense. Yeah, so you get the point. So you give it a better vector which has a probability distribution in it, a real probability distribution, and this gives you better gradients. And this actually arguably this trains you better, because if what you want in the end is to output a probability distribution like that, then it kind of makes sense to train on probability distribution like that instead of on one-hot vectors.
Yeah, in terms of training, you just take a model and take with the last layer outputs of the use it for the other model instead of one something.
Yeah, exactly. So does that make sense? Reward, does that make sense? Oh, hopefully. Okay. Yeah, so they say this works well.
I don't agree.
This should work well. And so let's go on. We have architecture spec. I think the table isn't very useful. but I have some highlights here. So like now we have a few minutes worth of talking about like random ML tricks they use in this state-of-the-art design. So they used some variations on attention, which hopefully let the model utilize the context window better. But like I categorize this anti-category random variations of attention, like and not really useful if you're not going to engineer a model. The next thing is cap and logits. So what we do is in each of our MLPs, I think. Yeah, I think at each MLP, we basically ensure that it's always bounded between like minus epsilon and epsilon. And this is basically the same sort of thing as gradient bounding. So in the same way that you can bound your gradients so they not explode, you can bound your logits. And like this is like, you know, a cheap trick which they use.
Sorry, could you relate what MLP is?
Yeah, it's a linear layer. Yeah, so and in this particular case, so MLP multi-layer perceptron, and like for example, they talk about that they cap logits in the final layer. So like we have like something, then we have the final classifier which turns our activations into the probability distribution, and like they just cap those probabilities essentially.
Got it, thank you.
Yeah. Okay. There is like an interesting engineering tidbit that this like breaks all the common libraries because none of them support that. But they also say that like we just trained with that, you can use it without that, and it's fine. Okay. Two remaining tricks. Like first is we use a tricky normalization. This is under my mental category of random normalizations. Like you can normalize by subtracting the mean. You can normalize by dividing by variance, and they normalize by like square roots of sum of squares divided by something, and I don't know, like some random applied math paper. And the final thing is group query attention. This is like very popular now. Apparently, I think it's used in Llama, both Llama 2 and Llama 3, and this too. Okay, that was a bunch of ML tricks. The next thing I'd like to highlight is that they train everything on TPUs. We had another seminar on TPUs, but for a brief recap, so like you want to multiply matrices real quick. Multiplying matrices is actually, a pretty well understood problem. So you can build custom hardware for that. In the same way as when Bitcoin was popular, at some point people started building like custom hardware for mining Bitcoins, and like it was very efficient for mining Bitcoins, way better than video cards. And Google does the same thing for GPUs because AI is the new crypto now, and they have like the GPUs are very cool. I suggest the paper, but like the takeaway that Google trains entirely on like in-house hardware for this, and they have like thousands of this in-house hardware in their house. Yeah. Okay. We actually accidentally already covered knowledge distillation. This is just a more complicated version of the formula I showed you, so nothing to see here. if you like apply the ML tricks, one thing which I find like interesting is that, so they say that our training emitted more than 1,000 tons of CO2 equivalent. And let me just real quick check how that compares to Llama, because they also report this number. So Llama,
Yeah, but I also Googled now. But Google is just the one vendor in the world.
that's not quite right. I mean, it's kind of a brand name. Maybe there are other people who are doing the same thing, but under different names.
A lot of stuff. A lot of specialized backward.
Okay. So actually, Llama 3 emitted like twice as much CO2. I think I'll take another, or let's say 15. Actually, yeah, there is a big benchmark section, which we can skip if you find it too boring. Yeah, so Llama emitted twice as much CO2, apparently because they trained like the 70B model and on GPUs. And GPUs are less efficient normally, and yeah. So 100 of which were offset by, I don't know what better sustainability program does. Hopefully they plant trees or something. Okay. Yeah, one other interesting thing is that they run like different hyperparameter experiments and then just average the models between different runs. This is fun. Okay, I think now we get to tables territory, and it's going to take us a little while.
Yeah.
Yeah, so this is a section called ablations, and ablations is a section you do when you have some idea, like claim, and you like remove core elements of your claim and run experiments and see if benchmark actually degrades. Because maybe your maybe the core part was actually something else or something less. So the first thing they do is they take this 3 billion model, and the Chinchilla paper says that you should train a 3 billion model on 10 billion tokens. Like this is a scaling law. And just for fun, they train it on 500 billion tokens. Because like, surely like this is like, we saturated everything possible here. And they get a 60 performance. I think this is perplexity something. Yeah, and I'm not sure actually. It's somewhere in the text. And distilled is better and also faster. So like this is hopefully something good. Oh yeah, and then we get to measure in perplexity. We just do a normal training and a distilled training, and again we are like better. Yeah, I think the other tables we can skip. They like try other different designs like group query attention versus some other attention, and find that group query is indeed better. So like they basically go through all the design choices they made and like try different and like see that there is indeed good. Okay. Yeah, so that was ablation. Now we are up to evaluation. I'd like to go through a few benchmarks they go through. Yeah, so this is an interesting claim. Performance of models trained in a similar way improved algorithmically with their size. I think this is against Chinchilla. I'm not sure. But anyhow, an interesting claim. This gives us like a form for this curve. Okay. So I think we can skip this table. This is something interesting. So this is LMC's arena and ELO scores on the arena. And the bolded things are Gemma. And what we see here is that Gemma outperforms Llama on the arena while being 27B. This is one legible thing. Another legible thing is that Gemma 9B outperforms Haiku, maybe with very wide error bars, which are wide because they just submitted recently, and so they have few ratings yet. And we have something weird, which is that some version of GPT-4 scores very low. I think this was spotted on Twitter early, and they fixed something, and the current GPT-4 is somewhere at the top, and GPT-4o is at the very top.
Thanks.
Yeah. So this is Chatbot Arena.
Okay.
Yeah. Okay. So I think I wanted to check a few sections from here. Yeah. So I just wanted to highlight that this table, this evaluation, where they compare Big Llama, Qwen, and Gemma, is exactly the same benchmarks that you do in Bad Llama. So this is OpenLLM Leaderboard version 1. And let me even show the Bad Llama version of this picture. So the Bad Llama version of this picture is that we have Arc, Hello, Slack, Melu, Trusko, Nay, Benagrande, GSM 8K, and indeed here we have those same benchmarks, except the truthful Q&A for some reason. Okay. And I think the final thing to highlight is that they have so they measure they have a custom benchmark which tests an ability of a model to go through a conversation, basically to go through a longer conversation where user asks a model to do something, because normal benchmarks are kind of one shot.
Yeah.
And I think this is it for the evaluation section. And for the safety section, so first thing they report is those toxicity benchmarks, which, toxicity is good to measure, but also we'd like to measure something else. And when they measure something else, they're like, oh, we measured how good it's at building nuclear bombs, but we did this on a random private benchmark, which we are not sharing. And it's listed in our literature section, but if you click through, it's oh, Mr. McKnight came up with this in an email. Yeah, so I'm a little disappointed here.
Something.
Yeah. They do better at offensive cyber. So this section is basically this is basically the same evals which they run in their in DeepMind's previous work, which is DeepMind's evaluating frontier AI models. So this is the same set of evals, just run on Gemma. And what we can see is that I think what this says is that Gemma is pretty bad at hacking. This is table 18 and table 19. Yeah, so I think that this is this has 63%, but yeah, but these are non-normalized numbers. So this 50% here is literally a toss of the coin. So like this means that Gemma is useless at looking at trying to find vulnerabilities at code, at least in the experimental design. But like what I'd like us to take away from here is that like that Google's state-of-the-art cyber evaluation suite tests CTFs on 3 data sets, 2 of which are not publicly available, and tests vulnerability detection. Yeah, vulnerability detection. I mean, like look through the code and tell me what the bug is. Yeah. Then they have a bunch of other evals which are about persuasion, which I'll skip for reasons of time. Yeah, I think this is it for this paper. And I suggest a few minutes break. All right. So now we have a second section of the day, and it is the so like we ended the first section on the benchmark they were evaluating Gemma on, and now we have another section, benchmarks. This is about like openly available and reproducible benchmarks of instruct models quality primarily. I'm distinguishing between base model and instruct trained model. Yeah, so there used to be a widely used benchmark suite developed by Hugging Face. It was open LLM Leaderboard. Apparently, 2 million unique people over the year it was available. They found that their benchmark saturated, and this is how it looks like. So like they started to approach like 100 everywhere. And this is a common problem in LLMs as they are rapidly getting faster. As a matter of fact, like if you open, say, if you open Vino Grande, or actually if you open Hella Swag, I think. Yeah, so if you open Hella Swag, it's like we show that it's still difficult for even state-of-the-art models. Published in 2019, and it was developed in again in response to the state-of-the-art models of that time saturating benchmarks of that time, and it was developed with adversarial filtering, where you literally like run a benchmark and see where models fail and only take these questions, basically. So like we needed to do another generation of that, and that's what we did. This was issue 1, saturation. Why we're doing something. Issue 2 is that some models were found to train on the benchmarks, maybe accidentally, because like the data leaked out on the public internet. And also one of the benchmarks was found, like benchmarks are exam questions, and this particular exam had mistakes in the questions. And the wrong answers Max is right. Right. So we take a bunch of new benchmarks, and I'd like to go through them like briefly. Yeah, so the first benchmark we take is evaluation of MMLU. MMLU is like exams across, I don't know, 50 subjects or something. And like some questions were unanswerable, some questions were too easy. And maybe let's take a look at the paper. MMLU Pro. Yeah. So a few things to highlight here is that like first off, we like MMLU Pro when we take a model and we evaluate it on MMLU and MMLU Pro, we get lower accuracy of MMLU Pro. And we should also kind of baseline expect that because MMLU Pro has like 10 option questions, while MMLU has 4 option questions. So random chance should kind of perform differently too. We demonstrate that MMLU Pro is more stable for different prompts. And this is how we demonstrate that. So we fix a model. We run the benchmark under 24 different prompts, and we so like the x-axis is accuracy. I think maybe normalized accuracy, something like that. And so like we throw dots at this line. We get a histogram, and we interpolate a distribution from this histogram. And this is what's going on here. And what we're seeing here is that MMLU Pro seems to be kind of, a more consistent estimator in that we vary prompts and it has lower variance across different prompts. So that's a good property. Yeah, and another thing I want to highlight here is that so on the right-hand side here, we see that on standard MMLU, left-hand side on the charts, there is little difference between chain of thought answers and direct answers. And the authors say that this is because MMLU questions do not require reasoning, like you either know the answer or not, or something. And there is a difference on MMLU Pro, and they say that this is because like our questions are hard and require reasoning. I'm not sure this is the case, but this is what they say. Yeah, this is it for this paper. And for the first benchmarks, which is the new one in the suite. The next benchmark is maybe more exciting because it's a PhD level benchmark. So let me get the paper again. So this is again multiple choice, but it is designed so that like PhD experts get low accuracy, and non-PhD people get low accuracy still, and GPT-4 is also not very good. And what's interesting about this result is this thing. So we get a normal person and we give them half an hour of Google and they still can't answer this question. So this is like maybe somewhat robust. And like it's in the name, like Google Pro benchmark, GPQA, Google Pro benchmark. I think, and like this is another thing which is fun, like so they are like do not reveal examples from this data set. Like they told this page, the authors of this page, like do not include examples, and like here is the canary string, which is like a special string you include into documents to find if this document is like a part of a blacklist when you filter your data set for training. Yeah. So that was GPQA. Now the next thing is multi-step soft reasoning, and like so this literally says algorithmically generated murder mysteries and object placement questions. So technically reasoning and long-range context parsing. Let's check the paper. So the paper starts with a novel neurosymbolic synthetic to natural generation algorithm, which I, like, personal opinion, parses bullshit. And let's try to decipher what that means. So this is the pipeline. Like, first they prompt an LLM to generate a mystery outline. Then they extract like the basic facts from this outline into like a bulleted list or something. Then they build out this tree, like, you have a fact that Sophia murdered Emily, and then they're like, top note of the tree, Sophia is a murderer. Like, why is she the murderer? She has a motive. Like, why does she have a motive? Like, because she has a grudge and like stole inheritance, and like, so they build out this tree, and then they validate this tree. Like, they just prompt LLM another time, like does like for each for each section of the tree, so like for each depth 2 node of the tree or something, we write a part of a murder mystery. This is LLM call 1. LLM call 2 is we like, does this part of the murder mystery include these facts? And if it does, like, we are golden. And this is a novel neurosymbolic generation pipeline. Yeah. And apparently this gives us like this is better than just asking GPT-4 to write a murder mystery, because GPT-4's murder mysteries can be inconsistent, and this process double checks and makes sure they're consistent. Yeah, and this is how they produce 756 murder mysteries, and which are apparently challenging to frontier models, because like you write like, I don't know, at how many tokens, like 1,000 tokens, not sure how many words that is. Like, okay, you write like a 10-word murder mystery, 10-page murder mystery. And so, like, to solve it, you have to connect the facts, which were different pages, and like reason and stuff and things. And this is apparently hard. And this is the core of this benchmark. We'll call it the MOO for murder mystery benchmark. All right. The next thing is math, the aptitude test of heuristics. One thing I want to highlight is that MMLU was designed by Dan Hendricks at Center for AI Safety, I think. Math was also designed by Dan Hendricks. So apparently Mr. Hendricks is an important person. Yeah, so this is a paper. Data set of 12,500 challenging math competition problems. And scaling transformers automatically solves other problems, but apparently not math. This is not exactly correct, because it solved like this paper from 21, and math, like lower levels, are actually pretty much solved at this point, but math level 5 is not solved yet. So we take math level 5. And yeah, so apparently the way that prior worked is that you have like a number of theorems, like this. What this theorem tells us is that you have a natural number such that it is even. No, sorry, such that it's odd. Yeah, and then there. Like and then like, yeah, they can like do an inverse of this, basically, right? So this like even a oddness thing. and we get a GPT to generate a proof, and you can just check with the theorem prover, like does it prove it or not. And apparently DeepMind was doing something similar. So this dataset is different because it's plain text and LaTeX, and it's like focused on like giving the same kind of solution that like a mathematics Olympiad solution would look like. And I find it endearing that this is how they validate it. Like a computer science PhD student who doesn't really like math gets 40% in our benchmark, while like a real math Olympiad person gets 90%. Yeah, so they say that this kind of design is good actually, because I'm a bit confused. Because why exactly? I mean, they cite a bunch of prior work about the theorem prover thing, and they kind of say that this saturates, but I'm still surprised. I mean, I'm very confident that if you like, if you ask hard mathematics questions and check them with a theorem prover, then you won't be saturated, else math would be solved right now. So I'm confused about this section, but for some reason they say that like showing like reasoning in the same way as like math Olympiad reasoning is good. Maybe what they are aiming for is that this gives us like a cleaner path to solving math, because math is currently solved with with some tricks which are best demonstrated in math Olympiads, and which are less, at least, yeah, like maybe it's still it can be useful to use a prover as an oracle, like that does this solve this thing. But data sets for provers are quite sparse as compared to math Olympiads, I think. Maybe that's the reason. Yeah, and like if you just scroll through the papers and you get like a bunch of stuff like rotate triangles, like cubic cross sections. So math is happening. One thing I'd like to highlight is that, so this was the actual benchmark which we use. But there is one other thing this paper does. It provides a pre-training dataset which you can use to fine-tune a model to be better at solving math. And the dataset is called AMPS. And what they do is they take Khan Academy and they apparently Khan Academy has 100,000 problems with step-by-step solutions in LaTeX. Yeah, and also apparently, oh yeah, actually I know that feature. So like Wolfram Mathematica has like a problems generator on a real bunch of topics, apparently from conic sections to KL divergence. And yeah, so like say you have like a bunch of generators for a bunch of topics, and they generate 5 million problems with just like different coefficients to train on. This is a pre-trained dataset.
They measure problems and solutions in bigger way.
Yeah. 23 gigabytes of problems and solutions. How many gigabytes of problems do we have today? Right. Yeah, and they say that pre-training on this thing enables a very small model to perform comparably to a 7B llama or something. Yeah, so pre-training is good when you operate in weird domains. I guess. Okay, that was math. We have 2 data sets to go. Next data set should be very clear cut, I think. Instruction found evaluation.
Yeah, because I tried to write some answer.
Yeah, I didn't know this. Sorry about that.
In good community. So you told us about the 3 data sets, but I don't understand. So in every data set, I'm not clear and understand what the goal of the guys who create data set. I understand data sets about, we want to measure safety of all, or we want things. Yeah, but like what the goal of MW or the use the data sets?
GPQA.
Yeah,
Right.
in goal of these data sets.
Right. So I mean, the ultimate goal is to measure how these data sets are about measuring how does a model, like how good a model is as compared to a human expert. So for instance, you can give MMLU to a high school student and they will like score like that. And GPT-4 will score like that. And a PhD will score like that. And the question which Leopold asks in situational awareness is like, when do we have PhD level, and when do we have like PhD across 10 subjects level, and when do we have like a superhuman across the board level?
Yeah, so it's like this, so time late and type critical. That's like person who finished it well, person who gave PhD in math.
Kind of. I mean, it does emulate. It doesn't emulate, but rather like it gives you. I mean, like MMLU is like the kind of questions like a doctor might answer on their exam, and then like which like so different kinds of specialists answer on their exams. So this is that. GPQA is the same but PhD level, again across many subjects, from molecular biology to like information security. So
Okay, and then the second question there is, so this is the article on Hugging Face when we started with the idea that we can't use our previous tests because now we reach around 100%.
Yeah.
But and this is the, as I understand, this is the the most useful, the most used test for LLM. But who decide, so who decides this LLM arena? So it's like who are decide what's test are better or not, or it's like how the process.
right. So I think that the way the way it worked with version 1 of the arena was that so there were a bunch of models, like you had Llama, you had like GPT-4. So you had like a bunch of models, and their like release papers said that like we evaluated on MMLU and this and that. And so one thing which Hugging Face did was just take these benchmarks and put them on an open leaderboard.
So IEPace just collect different data sets and run tests for like every major model. That's
And what they're doing right now is that they and the question, like, to answer the question, who decides? In this case, like, people at Hugging Face decided based on kind of industry consensus. And for OpenLLM version 2, I think they kind of unilaterally decided. I mean, they probably talked to like external experts and something, but like just they decide. Their benchmark, they decide.
okay. And this article is like a draft feature.
No, it's current. It was released like 2 days ago.
Okay.
Let me actually check that. Oh, actually, it's quite a bit more than 2 days ago. So a week ago.
1 week ago.
Great. Does it answer the question? Great. Okay. 2 more benchmarks to go. If eval, so it is really very simple. Like, this is the whole gist. Like, you give a model an instruction, like, write in more than 400 words. Then just like take len of the output and check if it's 400 words or not. Or like mention AI 3 times. Like, if AI is not 3 times there, it fails. Yeah, very simple benchmark. Give a model instructions, it either like verifiable, easy to verify instructions, it abides or not. Then there is big bench heart. Yeah. So let me actually go through this summary first. Yeah, so big bench hard is multi-step mathematic reasoning, like understanding a Boolean expression, detect sarcasm, kind of an entity extraction when you have like 2 people by the same name in a situation and you want to figure out which is which. And from ARENA results, we know that it correlates with human preference well. And just one thing I'd like to highlight from this paper is that they in 2022 they show that on these tasks, like on big bench hard, chain of thought matters. Like, this is 0 is yeah, I think 0 is baseline, is human baseline or something. Oh no, actually not necessarily. Like, yeah, basically just normalized so as to show like performance difference. We get that chain of thought improves our performance. Yeah, I think that, another thing I would show here is that so here rater is a human completing the tasks, and what we're seeing is that that small models, other one is OpenAI's first model ever, that small models perform at random chance, and that 500B models were actually used in 2022. No one does that now. This trend towards lowering I mentioned. Yeah, and like chain of thought gives us like like at 15% increase or something, 20% increase in this case. And on some cases, this is like what the interesting thing. I'd like to highlight that. So on some cases, it actually makes things work. Like they didn't work when we increase model size without chain of thought, and they start to work when we add chain of thought. This is like the actually interesting case. Great. I think this is it with Big Bench. Yeah, so here they show some criteria, how they show them. I think it's fair to summarize that as we showed them because we think they're good. Yeah, so like these are widely used, these three. These two are good according to experts. The metrics are clear cut. These are not used in training datasets yet. And they correlate with human preferences. And we want to measure mass. Great. I think I want to show two things. Okay, yeah, so I basically want to show the figures. So figure 1, they normalize scores so that random chance is 0. Figure 2. Quen is at the top of the new leaderboard. I think I need another 6 minutes. Quen is at the top of the current leaderboard, and I find this like quite interesting because what this tells us is that a Chinese model is at the top of the benchmark.
It's recently with benchmark.
But it was actually pretty good before that as well.
And where are the major models? Where are the major models?
So this is Llama 3. I mean, like major model 1, Llama 3.
Sorry, is it just one open model?
Yeah.
Okay.
Yeah, so like Llama 3, Phi 3, the others are small. I think this is like some like weird experimental thing, like by some weird people. I don't know. Yeah. Also, this is kind of a little interesting. It's kind of hard to interpret, but I think if you really squint, then what you're saying is that at the top we have like kind of models by major labs, and they increase in ranking. And at the bottom you have some weird models sometimes, like Upstage Solar or like Alpha Monarch or Beyonder, and they decrease in performance in ranking on the new leaderboard. So the new leaderboard seems to favor major labs. This might be speculation here because those weird models fine-tuned on the benchmarks. Right. Now we have a correlation heat map, correlation between different benchmarks. What we're seeing is that Big Bench correlates with MMLU like real hard, which kind of sort of makes sense because both claim to reason multi-step reasoning in like exam-style questions. So apparently, like they measure a similar thing. GPQA correlates with MU Pro as well. GPQA is PhD level, so maybe also multi-step reasoning. Yeah. And yeah, 4 figures to go. Figure 1 to go is, unsurprisingly, we see that instruction-tuned models are good at following instructions, and base models are not so good. Now we plot MLU Pro and GPQA is a function of the old MLU, and we see they correlate reasonably well, which is kind of good news because MLU Pro is kind of a filtered and expanded version of MLU or something. And this also means you can kind of like connect the previous benchmark results with the current benchmark results by fitting like an order 3 regression or something. Yeah, the same with mass as version of the old mass benchmark. And we see a few weird artifacts, like some models scored 0 before, but score good now. And some models scored high before, but score 0 now. This is weird. Probably a technical issue. And the final thing, final? Yeah, final. So red is old, and like the blacker the like yeah. So from red to yellow is more current, and then black is very current. And what they're seeing is that people used to have like 180 billion models, and no one does it anymore. Except NVIDIA, we just released a 340 billion model, which no one cares about. Yeah. So this is OpenLLM Leaderboard version 2. And we may or may not update Bedlama for version 2 when we release Bedlama version 2. Yeah, that's it. Any questions about that? Beyond the ones we covered already?
I didn't hear the last graph.
Let me open that back. Yeah.
Yeah. So I expected that all new models will be like will higher performance score, but they are with lower performance score.
Yeah. So if you just look at colored dots, then this is happening. Like the reds are generally lower than yellow. Yeah.
Black it's lower. Definitely lower.
Yeah. Just bear with me. Look only at colored dots for the moment. Colored dots do show this pattern you're talking about. Like before October 23 is low, and like March 24 is very high. And then what happens is we change the benchmarks. And our benchmarks are specifically designed to be harder.
You benchmarks of the same blood.
Yeah.
Okay, I got it.
Also, I can recommend like a data visualization and good chart practice book.
I mean, there were no one separate one book. No.
Well, I have to just make drop.
I mean, I'm reading one now, and I think it's pretty good.
We'll get send it to the.
Yeah, but I'll get that shortly. Any other questions for that? Okay. I think we're done. So thanks everyone.